All right, ladies and gentlemen, welcome to ComSci Connection. Today's topic is interfaces. Now before we go and look at the stuff that I've drawn on the board, I'm going to go ahead and explain what an interface is. Some of you may be familiar with the term GUI or graphical user interface. Just to clear any kind of confusion out of the air right away, this is not that. In fact, it's really far from that. Graphical user interface is what you work with when you use a program like Microsoft Word. It's there to keep it nice and pretty for the average user so they don't have to see the code and all the mumbo jumbo that goes on in the background. We don't want to see that as users. As programmers, we are going to talk about a completely different thing when we talk about an interface. Basically, the simplest way I can think to explain it is it's more or less like a guideline or like a rule that classes must follow that you derive from the interface, or that, as we say, implement the interface. So a condition is really, condition is my example. An interface is really just a behavior or a specific set of rules that any derived class must follow. Now, what is a derived class? Well, an interface itself is not a class. It's an interface. You cannot instantiate an object of type interface. In other words, with my condition example here, if I had a class or an interface called condition, I cannot create a condition object. And, condition C equals new condition, for example. But I can create derived classes from the interface condition in this example that would allow me to use condition as a guideline to the behavior of those classes. Now, I know that's probably really confusing the way I just explained it, so let's just go ahead and look directly at what I've got on the board here. So, to start out with, let's ignore what I have at the very top, and let's look specifically at this. This is a small kind of diagram for what I've got for my interface. It says condition, there's an I in parentheses to signify that it's an interface, and then it says that we'll have the method accept. Now, the code for this is here, and yes, this is complete, except for one thing. This, if you put this into a compiler, would actually be a complete file. It's a complete interface. I keep wanting to say class, but it's not a class, it's an interface. You can't create an object of type interface, in this case type condition. But it seems weird to people the first time they see this when you realize that there's no body to this method. We've defined a method here, and in fact that's the correct terminology for it. We have defined the method public boolean accept, taking in a string as an argument, calling it s, but something seems missing here to us, right? Where is the body? Where is the implementation of this method that we've defined? Well, that's the key to an interface. It doesn't have one. In fact, it never will. You cannot implement any code at all in an interface. So what's the point of all this? Why would I define this method called accept, taking in a string that returns a Boolean value and is public if I don't know what it's going to do, right? Well, I just told you what it's going to do, right? It's called accept, that's how you call it. It takes in a string of type S, and it returns a Boolean value, and it's public, so it can be called from anywhere. That's the rules that we know our derived classes must follow. Anything that's derived from the condition interface must implement this method. So why would we ever do this? Why would we ever use this? Why not just create classes that have this accept method and not use condition at all, or an interface at all? Well, the answer is very simple, actually. We're going to look at what I've written at the top of the board. So this method, we obviously don't have a body for it. It's just for your imagination. We don't care about how it's implemented. But imagine that this was in code somewhere else, right? And we're going to use our condition interface. Let's analyze this method header here. We've got public, which means it can be called from anywhere, and it returns type array list of strings. It's called getAccepted, and it takes in arguments of an array list of strings called orig, and a condition C. Well, that seems weird. I mean, didn't I just say that you can't have a condition object? How does that work? Well, the point is, you can't have a condition object that is a new condition, quote unquote, but you can have a condition object that is one of its derived classes. What does that mean? Well, up to this point, we've seen things like this. Just as an example, we've got something like string s equals new string, right? We've all seen this, and we've all maybe wondered, or maybe we've asked if you were really curious, but why is this written twice? Why do we have string and string? This seems kind of strange, right? I mean, why would we need to define that it's a string twice? It's really redundant, and it just seems unnecessary. Well, in fact, it is very necessary, actually, because if we understand how this is actually stored and how it actually behaves to a computer, we've drawn memory diagrams before, and I will do that at some point in this video. But simply put, I'm going to explain that the compiler. This is basically what the compiler knows the object is. And this is what the object actually is. I will go into more detail about this near the end of the video, but this left side argument here, string in this case, says to the compiler, I'm going to put a string somewhere, and it's going to be called s. And whenever I refer to s, you need to understand that this object, s, is a string. That's what the left side says, ignoring the right. That's just what the left side says. It says, I'm going to store this thing called s, and whenever I refer to it, you need to understand that it's a string. Well, what does the compiler gain from that? The compiler knows what a string is, right? So it knows what methods it can call. So it's not coincidental that when you later say s dot, and it pops up with those fancy lists of things you can do, like length, or replace all, or char add, or whatever, these are all functions the compiler is aware that you can do because the string class defines that you can do that. What it actually does in this case happens to be the same because it is actually a string class. You don't really think too much about that because that's the behavior you expect. And we only tend to notice when behaviors don't go the way we expect. If everything worked perfectly, if you hit all green lights from here to wherever your destination is, you're probably not going to complain. You're not even really going to think about it. If you hit every single red light, then you start to complain. The point is that works like magic. But really, the compiler knows that the magic will work because it knows that it says it was a string, and it also knows that it's never going to allow you to assign an object type to something that it thinks is a string if it's not a string. Like if you tried to put dog here or whatever, it's going to say dog is not a type string. You can't do that. So the compiler is happy because it allows this line, knowing that, oh yeah, you said you were going to make a string, and then you put a string there, so that's great. And then later on, when you call s or refer to s, it knows you're referring to a string. And because it checks these things, you are referring to a string. Magic. In this case, we can use our condition object to manipulate this behavior. So let's go ahead and derive some classes from condition. I'm going to keep these really simple because there's no reason to get all complex. So I'm going to make a class, I'm going to abbreviate it to BWJ, but it begins with J. So basically any string, because we know that it must implement this method, right? This the interface tells the compiler that it must have this accept method, but it hasn't been implemented yet. So we have to implement it here, otherwise the compiler will not allow us to actually complete this begins with Java class. Or begins with J, excuse me. And also, I'm going to create another drive class, and I'm going to call it, I don't know, begins with L. So this has an accept method and begins with L because it has to, and begins with J also has an accept method because it has to, because the compiler will not allow you to create those classes and to put the keyword implements condition after it unless you have implemented condition. And in this case, condition says that you must implement this accept method. So now, what does this mean? I mean, I've been talking for a long time about all these things that I haven't made any connections. Well, it means this. It means I can do this. Condition C equals new begins with Java. Bam. Magic, right? It knows that it's a condition object on the left side, so it knows that you can call accept on this. When you actually create the object and then return it to this point, it'll say, well, yeah, I'm happy with that because it begins with Java, implements condition. So therefore, because I know that I can't ever create this class without fully satisfying the requirements from the condition interface, I cannot possibly, it means that it must have the properties of a condition object. So it's perfectly happy assigning a begins with J object to a condition because a begins with J object is a condition. It's just a derived condition. Now additionally, I could have begins with C, begins with A, begins with B, and I could have maybe another, like a derived class that begins with Java that only accepts lowercase, I keep saying begins with Java, begins with J, that only accepts like maybe lowercase j's, but rejects uppercase j's. These are different behaviors that you can implement. What does this allow us to do? It allows us to pass objects that are derived classes from our condition interface to standardized methods like this that take in a condition object. That means that we never have to change our code, and we can get completely different behaviors from the same method depending on which object we actually pass at the time that we call the code or the method. So I just regurgitated a lot of words there, but what that really means is that I can make one method called getAccepted that does these things. We don't care what it does, it doesn't matter for the purposes of this example. But we know that if I take in a condition object, it must be a condition object, otherwise the compiler won't allow you to send it. The compiler will say, this is not the right argument type, I require a condition. So if I try to pass it a string, for example. But if I pass it anything that's derived from condition in the same way that it can check this against this, it's going to know that, yeah, it begins with J is a condition, so therefore in this method, when I say C dot, it's going to pop up a list with all of the methods that we can call, and in this case, that's going to be this one, accept. So it knows that it can accept things. It doesn't care what it actually will do, because what it actually will do doesn't matter to the compiler. All the compiler cares about is, have you satisfied the requirements on my end? If you get problems at runtime, that's your problem, and the compiler doesn't care. But in order to satisfy the requirements for the compiler, and therefore for this method, you would actually have to pass it some object that is a condition, whether or not it's a derived class or a derived class from a derived class or whatever. As long as it has the properties of a condition and therefore is a condition, then it's perfectly happy. So the short answer to why would we do this, just to reiterate, is that it allows you to write code once. You can implement this method using this c.accept method. What did I write? Accept. And then you're guaranteed that regardless of whether or not you send it a begins with J object or begins with L object, or later on, if you come in and implement 735 other condition objects that all implement condition, you're guaranteed that you never have to come back and change this code. It'll always work regardless of what you're doing. And that's the magic of interfaces and inheritance. This is the key. And we're allowed to do things like this. So I can send an array list of strings of all names of all the people in ComSci 228 at Iowa State University in 2013, and it's going to immediately, I can send it begins with J object as a condition, and then it'll immediately return all of those names that begin with J. Similarly, I could send it a begins with L object as a condition and the same original list, and it's going to return all names that begin with L. And I never had to come in and change the code. The code changed when I implemented these classes. The rules or the parameters that the interface that you must implement if you're actually going to implement the interface haven't changed. So the interface hasn't changed, and therefore our code doesn't need to change. The only time I'd ever have to come in here and change this code is maybe if I change my interface. So that's the short answer. Now, how can I remember this, Jesse? You've just talked for God knows how long and said all these crazy things that don't make much sense, and it's just a lot of hot air. How can I apply this And how do I take this home? I'm going to erase all of this because this is what you need to take home. This is the important thing I'm going to say. And if you can remember this, you'll be perfectly happy with everything. Shout out to Brandon Maxwell, by the way, for this little tidbit of knowledge. This is what solidified it in my head. So when I say something like, yeah, I'll use a basic primitive example. Pet P equals new dog. Okay, this don't match, pet and dog, but pet's an interface. What if I told you that pet was an interface? And that dog implements the pet interface. And pet has a method called, that's probably too high. Pet has a method called, I don't know, get name. Or no, let's do speak. Some of you may have seen a similar example to this before, but it's pretty primitive and that's why I'm doing it. So if the interface pet implements speak, and then the dog class, for example, has a method called woof. The left side of my arguments define what the compiler can do, because this is what we call our compiler type. So it tells the compiler what we can do. We also call this a static type because it cannot change. So it's static. Compiler type, static type, tells the compiler what it can do. So it tells the compiler that pets can speak because we implemented speak, or we defined speak, I should say, in the pet interface. So pets can speak. A dog is actually what this object is, so it's what this object will do. It's what we call, here, box this up to be consistent. It's what we call our dynamic type because it can change. It's also what we call our runtime type. Time type. Chalk's running out. So basically, it's a pet, right? So the compiler knows that it can speak. What it actually is a dog, but the compiler doesn't care, nor does the compiler need to know. It doesn't. It knows that when you wrote this line and put the semicolon there, it didn't underline it in red because a dog is a pet. But when you actually run this code, that's when speak is called. It's going to refer to the dog class to execute that code. So that's what it actually will do. So a dog might bark. But a dog also has a woof method. But if I try to say p.wolf or woof, it actually will underline that in red because it doesn't know that it's a dog. Even if this was a line in my compiler in main, and it was the only line, and right below that I wrote p.woof, you'd say, well, it must know it's a dog. I just wrote that it's a new dog right above it. Why is my compiler so stupid? Because it's a machine. It's a compiler. It doesn't know. It doesn't know. It's not smart enough to know that even though you just said new dog, it doesn't know it's a dog. It's that stupid. All it knows is that you said it was a pet. Now, if I put dog here, dog p equals new dog, yeah, then great. Call wolf on it all day long because the compiler knows that it's a dog because you told it it's a dog. This is where you tell it what it is. It doesn't care, nor does it know or has any way to find out. I'll take that back. But it won't. The compiler itself will not ever worry about what it is. Now, if I change this, if I had pet p equals new dog at one point, and then later on down the line, I'm going to erase these names, leaving the big boxed in ideas there. Later on down the line, maybe I do some stuff with my p. I can then do this, p equals new cat, and this chalk sucks, so hopefully you guys can see that. P equals new cat. Well, cat, let's assume, also implements the pet interface. In this case, it will work. Do you notice that I haven't changed P? Just like string s equals new string, and later on you can come and say s equals new string. I can do that, and I made P equals a new cat. It's still a type pet. In fact, it can't change from a pet, remember, because it's a static type. So it always is a pet, forever. P is always going to be a pet for this program, and you can't ever change that because you defined it as a pet. And that's what the compiler knows, and that's all it's ever going to be happy with. But later on, you can change P to something else as long as it is a pet. And in this case, it's a cat. So if I write p.speak here, or I write p.speak here, I'm going to have completely different behaviors. And this is a preview of polymorphism. This is not inheritance. Polymorphism is going to be for another video, but this is really what I want you to take away. Can do, will do. Can do, will do. Can do, will do. That's all I have to say for this. See you guys next time.